I'm George Mason. If you don't know, it's very close to Washington, D.C. It's in Virginia. We often try to downplay the connection because the city is such a mess, but Northern Virginia is the best place in the United States. Which is, what everybody says about wherever they live, right? That's always the best. How can I support the claim of it being the best? It's has the best school system, public school system. So it's always ranked 1, 2, or 3 in the country. We ignore the years when it's 2 or 3 and just pick on the years where it's ranked 1. It has the best high school in the country that is ranked the #1 high school 4 out of 5 years. It's a magnet school. Thomas Jefferson. It has the highest average family income, not rich people, but people who make high salaries. Highest education level, there's often a correlation. I think I read that 85% of the adults have college degrees compared with almost 30% nationwide. And what is it, 25% have masters, and there are something like 50,000 PhDs. So having a PhD does not make me special at all in Northern Virginia. What else? Oh, there's everything in the world for kids, but it all costs money and it takes a lot of driving. That's the other thing. Anyway, so it's also one of the most diverse places. And George Mason University is known as much as anything else for the diversity. We have a larger variety of people from everywhere in the world. And it's not just people directly from elsewhere, but we have a very large immigrant population. So the biggest subgroup is actually Vietnamese Americans whose parents moved to the United States in the 70s or 80s. And there's a lot more. So anyway, Mom had asked me to talk about mutation analysis, which is more interesting than Fairfax. We're going to go through several things. Since this is the first part of the day, I'm going to talk a little bit about coverage criteria in general, talk about mutation in general. I'm going to try to give it a high-level overview as opposed to specifics, and some of you may have seen some specifics. I'll get to that in a minute. And then talk about using it for source code, which is the classic and the most commonly known, and then another use of mutation for generating inputs. And then we're going to close this session later this morning by talking about some of the research that's ongoing. Since we're all PhD students, I thought it would be very interesting for you to see what's happening in the field research-wise, and we'll talk at the end about what might happen in the future. In case you're interested in this, what might be interesting. So I want to have an open discussion at the end of what you're interested in, what questions you have, what you think might be interesting as far as research around mutation analysis goes. And the first thing, I'm just going to overview my background. I want to ask a little bit about your background. So this is, if you're in the hotel room bored, you probably were looking up some of the speakers. So this is probably pretty boring. The main thing is I've written a lot of papers. I was talking earlier, with one of the organizers, one of my things is balance. Computer science has become, from a fairly inclusive, diverse area, has become a very exclusive and non-diverse field. So our senior level courses, for example, at the most diverse university in our country, is about 85% white and Asian males. I've tried to work on that. Several people are trying to fix this. We actually have a higher percentage of females in the room. Look around. It's not obvious because there's still a minority in this room. But a higher percentage than a lot of PhD courses. So about half of my PhD students have been women, and we're really pushing on that, particularly with some of our earlier courses. One of my current projects is about education, about how to teach intro programming. And we're bringing in some things that we hope will make it a lot easier to teach large numbers of students, which is a problem we're having with increasing enrollments, as well as increasing diversity in the field. Partly because industry begs us all the time to graduate more diversity. Let's go on and talk about coverage criteria. So I'll look at those at the break and get an idea. So since Mom had put me first, I thought I'd make sure everybody has some sort of basis in some testing, and mutation is one type of coverage criteria, so I want to talk about that in general. And I'll start with some simple definitions. I'm going to go pretty quickly. If I'm going too fast, wave at me or something. These are fairly fundamental. These are IEEE terms, so these aren't words I'm making up or definitions I'm making up. So a fault is something that's wrong in the software. You can point and say, this is wrong. Okay. It may be one particular location. It may be distributed in some locations. It's usually pretty, we kind of think of it simple. I'm going to come back in a minute and talk about how it can be more complicated. A failure is something that happens. It's the behavior, it's an output, or we take the wrong path, or an exception where we get a runtime exception is a failure. An incorrect value on a screen is a failure. They're related, and they're related because they're related through software errors. So an error is an incorrect intermediate state. So a fault can create an error state under some circumstances. We'll talk about that in a minute as well. And then that error state may result in a final error state, which is the failure. Okay. We may or may not see a failure given the fault. We may or may not see a failure giving an error state. But an incorrect internal state is an internal variable that has the wrong value, or the program pointer. We take the wrong branch, so at the wrong place in the program. If you take a compiler class, you can think of that in terms of the program counter being wrong. It's important to note that software does not degrade like hardware. So eventually, the little buttons on my pointer will wear out, or my diode here will wear out, and it won't show a picture of the batteries, obviously die. Software doesn't do that. Any faults in the software are there from the beginning, so they're more like hardware design mistakes in that sense. You can model that in a more complicated way. It's also important to notice that when we test software, we can find faults if they're there. Okay, they're always there, but if they're there. But we can never prove that there aren't any. And that's a simple halting argument. So that's a basic theoretical concept in testing. The only way to show that there are no faults is if you try every single test. And there are lots of them. So that leads to what's called the Ripper, or originally RIP model. So this is sometimes called the fault failure. This was defined back in the 80s. Well, the first three were back in the 80s. The revealability has been added more recently, mostly as a result of test automation. So reachability means we get to the place where the fault is. So if there's a fault in the program, how do we find that fault? How do we observe that fault? Well, we have to get there. Now I said location or locations, because sometimes a fault may be distributed over several locations, sometimes close, sometimes far apart. It's also possible that for some incorrect behaviors, there are multiple ways to fix this, right? I can change the loop control, or I can change the way the loop is structured, for example. So there may be, for the same problem, underlying problem, one person may say, here's the fault. Somebody else may say, it's a different fault. Okay, so it's not always so simple. But that's fine. That just complicates. We try to think of it in a simpler way, but you have to bear in mind it is a little bit more complicated than that. But we still have to get to wherever the faulty problem, where the faulty location is. Then we have to infect, so that's called reachability. Infection means the state of the program has to be wrong. Okay, after we get there, so a variable has the wrong value, or we take the wrong branch. Those are the usual cases. So then we say the program execution is infected. That infection then has to propagate. So that's the RIP, which means some output or some final state of the program has to be wrong. And finally, the test has to be able to observe the incorrect portion of the output state. It has to be revealed. And this became important when we started automating our tests. So in the old days, we'd run a test and humans would look at the screen or the printout or inspect the database, and we kind of had in the back of our mind, we're going to look at everything. Well, now we usually automate our tests with JUnit or some other framework like that, and we put in an assertion or a statement that checks the state. right? So how many people have written JUnit tests? Okay, good. It's common now to be taught in the first 2 or 3 programming classes, JUnit. So if you're not, a couple of you didn't raise your hand. If you're not familiar with JUnit, you need to be familiar with JUnit. It's not just about testing research or test practicing. It's core basic software development now. I mean, I said JUnit is one particular technology. There are lots of test framework technology. JUnit is just the most ubiquitous. It stands for Java unit testing. I think most of you know that. So anyway, when we're out of JUnit, we have the test, and then we put in assertions that say X has to be greater than 10, for example. And the assertion gives does one thing if the assertion is true, another if it's false. That is, if the test passed or failed. So we have to reveal the portion of the incorrect state. I think a picture makes this a little bit clearer. So if we have a test up here at the top, then we need the test to reach a fault. So that's the reachability. Then that once we get to the fault, then it has to infect the program state. So something has to be wrong in the execution. That infection has to propagate to an incorrect portion of the final state. Particularly when we automate our tests, we can't look at everything. And in fact, we never could. If we're putting something into a large database, we can't inspect the entire database every time we run a test. It's simply infeasible. It's too large. If we're sending a dozen signals out to different devices, we probably can't check all of the signals. So each test has to look at part of the final program state. So it propagates to some part of the final state is incorrect. We have a screen, there's one item up here that has the wrong variable, or the wrong value. Everything else is fine. So then we have a test oracle, which is an assertion in a JUnit automated test or in some other automated test. And it looks at the final program state, but it doesn't look at all of it. It looks at some of it. By the way, just as an aside, one of the things we found, so some of this came out of one of my recent PhD students' research into test automation. One of the things we found is that our undergraduate students, were very bad at writing their JUnit assertions. That is, their JUnit assertions often had nothing to do with the test. So we tried this in our graduate software testing class, which is a master's level class. About 80% software professionals who are working part-time on their masters. They weren't any better. In fact, they were a little bit worse. Their assertions were a little bit worse than our sophomore undergraduate students. So then we went out and we evaluated tests from about 25 people from 3 different companies, professional testers, software developers. They were worse than any of our students. Their assertions were horrible. They seldom checked anything that had anything to do with the test. So their tests were, a lot of them did the one thing we call the stupid testing, which is they just check to see if the program blew up, if there's an exception. So anyway, so you have to check, so we can only check part of the final state. We only reveal it if the state we check overlaps the incorrect state. So that's the revealability. And we think the students did better. Again, we think, that's our opinion. It was because they actually had been taught something about writing automated tests. Most of the people who were doing it for a living learned on the job. So how many people took a software testing course as an undergraduate? I guess not very many, yeah. It's very rare. That was one of the questions there. It's very uncommon, but yet that's half of what industry spends their resources on. Half. And we don't teach people anything. So RIP is old, 80s. Ripper, adding that one, that's fairly new. Mom had mentioned that our testing book that Paul Hammond and I wrote, second edition comes out in October, and it has this. The first edition just had the RIP in there. Okay, now I have another problem for you. Since you could do this, you might want to do this on a separate sheet of paper since you're going to turn in the other, or you can turn this in, I don't care. You can work with a partner or two, but I want you to think about this in this context. So we have a small program over here that finds the last index of an element in an array. So we have an array X, we have an integer Y. We search through the array. If the current element matches the current element in the array matches the element we're looking for, we return the index. If we don't find it, we return -1. So I want you to do, let me just make a little shortcut. Describe the fault, including a change to fix it. So here's the fault. We start at the end of the list. X equals, from I equals X dot length -1 to I is greater than 0. Anybody notice anything funny about that? Yeah, we don't check the 0th element. We don't check the ground floor in Sweden. It should be greater than or equal to. So that's a very simple, very easy fault. We've all made that in C, I'm sure. So I want you to write down test values that does not get to this fault. Write a test that gets there but does not infects but does not propagate, reaches and infects but does not result in a failure. So the output is still correct. Okay? Okay, I already gave A, right? It should be, we need to check the 0th index. So what about B? How do we not reach the fault? So those are two good answers. A null value for X, so X is null. Then it doesn't do the check. And it throws, in fact, it throws null pointer exception. That was one of the comments, right? What about reaches but does not infect? So reaches just means that we carry out the test, right? So if Y is there, but it's not in the 0th position, so here's a test, right? So we do the check. So we look at number 5, or we do the check first. Then we look at number 5, compare. Then we do the check again, so we've reached the fault twice. And we return 1. So what about infecting but not propagating? It's not in the array. We look at the final iteration. So here we don't look at the final iteration, so we don't infect. But here we look at this one. We don't look at this one because it was wrong. So we infect by not looking at this, but it didn't matter. Infect means that we take the wrong path or we assign an incorrect value to a variable. So we should have done one more loop iteration. Yes, so we should have done one more loop iteration. So we didn't do that, so we infected the state by not taking that loop iteration. Yeah, so that was a little bit more subtle, and giving you 3 minutes actually is a little bit pushy, unfair. So I don't expect everybody to get that in two minutes. If I waited till tomorrow, I think most of you would come up with that. So finally, reach, infect, and propagate. I think that's maybe the most obvious. So how do we actually see a failure? Yeah. Yeah. So the value we're looking for is in the 0th spot in the array, and we're not going to see it. So we would expect this to return 0, but it returns -1. So our assertion on this should be on these tests should be the value that's returned. That return value is either -1 or it's some index value. So the whole point is the Ripper model is important, and it becomes more important in mutation. We'll come back to that, by the way. But it's a little bit subtle sometimes, and there's some little complications even in a short, simple program like this. When people have more time, and when I do this in a real class, I'll give people, this is a common homework assignment. People have more time to think. The one that people actually stumble over the most is B. How do we not get there? And it turns out that for people who haven't really studied testing, those are the kind of tests that they often forget about. How many of you have heard the term happy path test? Okay, so it's an informal slang term. Happy path means we test what's normally supposed to happen, right? Most people who haven't had a lot of education in testing will write a lot of happy path tests. They'll check the things that usually happen. Where you find the most mistakes, by the way, are unhappy path tests, exceptional conditions, or unusual situations. So those are the tests that people are less likely to come up with unless they have a lot of training or a lot of insight or experience, or unless they're following coverage criteria. So this is a happy path test. This is a happy path test. This is clearly not a happy path test. This is an unusual situation. So, you know, a happy path test, you're trying to find something, walk around a new town. Well, what about, you have a map, what if there's a huge construction site? That would be an unhappy path test, so that's an unusual situation. So we had to walk around the construction site to get to this building, for example, today. And that wasn't in the path, but not surprisingly. Okay, now let's talk about coverage criteria. So, and that's one of the goals of coverage criteria, is explicitly to help you find happy or unhappy path tests. The most important point is we can't use all inputs. Even a trivial program like this, where we have 3 integers, we're finding the average, well, it turns out you have over 80 octillion possible tests. That's a lot. So it's not infinite, this is finite. You'll hear people talk about input spaces as being infinite. Technically they're not, because it's a finite word size, finite memory, blah, blah, blah. But for a practical tester, what's the difference between infinite and 80 octillion? I'm going to die before I finish running the test, so it doesn't matter. You know, 80 octillion or infinite is essentially the same. What we're doing as a tester is we have this huge input space to our program, and we're trying to search it in some way. That's really our goal. And what coverage criteria do is they give us a way to search that input space in a structured way. A lot of testing is done, it's called human-based testing, where I think, okay, what might go wrong with this program? Let's try some things. If you're really experienced and you're very knowledgeable about how software works, what programmers do wrong, and you have really good insight into logical thinking, analytical thinking, and understand the domain, you can do a really good job human-based testing. There are not that many people who are good at it. In fact, a very small percentage of trained professional software testers are actually good at that. Criteria help direct you into a way to find lots of good tests. So how do they work? Well, a criterion is just the rules and a set of rules in a process. The most common is cover every statement. You've probably heard of that, statement coverage, or node coverage in a graph. Test criteria give you test requirements. A requirement is something you have to do. So the coverage criterion, cover every statement, means every statement is a test requirement. Okay. It's very simple. It gets a little bit more complicated, but it's very simple essentially. Every functional requirement I want to check at least once. Well, every functional requirement then becomes a test requirement that I have to try that. The problem with this one is we very seldom get all of our functional requirements down on paper. In a complicated system, we're lucky if we get 3/4 of the actual requirements that we care about. The others appear during design, development, and testing and use, but they're almost never written down, so that's an issue. If you look through the research literature for the past 30, 40 years, you'll find hundreds, thousands of test criteria. But a lot of them are exactly the same. So we have statement coverage, we have node coverage on finite state machines. They're the same thing, cover nodes in a graph. Paul Amon and I found over 50 definitions of node coverage on a graph. But every graph was a little bit different, so each person wrote a different paper. So they're really just a few. And we can only find 4 structures. So when you take a discrete math course preparation for computer science, you study these discrete structures. This is why, so you can do testing. Criteria on sets of input values, criteria on graphs at every node, every edge, etc. Logical expressions, we have logical expressions everywhere. And what we're going to talk about today is mutation, which is a criterion defined on a syntactic structure, generally a grammar. And there are other ways to describe syntax, but most of the time it's some sort of grammar. This fits in these types of structures and criteria fit into the Ripper model like this. Input domain testing, we're looking at sets. It doesn't ensure anything. Graph testing makes sure we get places, reachability. Logical expression testing goes a little bit more deeply into the expressions. That ensures reachability and infection. Something has to be wrong. Essentially, the predicate has to evaluate differently. And then syntactic structures ensure we have to get a final output that's incorrect. So that's sort of the organization of the classes of test criteria. The only criterion I know of for based on syntactic structures like this is based on mutation. So I guess you could define it so that, in fact, there's a version of mutation called weak mutation that only requires infection. And I plan to sort of talk around that towards the end. But that's the only one that requires it to go further than just infecting. But you're right. You could define syntactic criteria without doing that. Okay, how do we use test criteria? Well, there are kind of two ways. We have criteria and a bunch of test requirements. We satisfy the test requirements by designing tests. So we design tests to cover every statement or kill all the mutants. That's sort of obvious. Researchers look at that. You really need a lot of automation to do it if you have anything beyond very simple criterion. The other way is you generate test values some other way, and then you measure them. You evaluate them against the criterion. So I have a criterion that defines 50 test requirements. How many of those test requirements have I satisfied? Oh, I've satisfied 45, so I have 90% coverage over my, excuse me, over my test requirements. This is more common in industry. The confusing part is, what does it mean if I don't have 100%? What if I haven't covered all my statements? What if I have 90% statement coverage? It means 10% of your program has never been tried. That's kind of scary to me. If I'm getting in an airplane where 10% of the code on that airplane has never been run, I don't feel very confident. By the way, 10% is pretty common on most airplanes. Trains are a little bit worse. They're not tested to the same level, but that's pretty common. So think about that on your way home. How many people are flying home? You're more likely to survive a train wreck than a plane wreck, actually. Because of this, there are sometimes we're measuring. Sometimes people call them test metrics instead of test criteria, so it's the same. If you hear the term test metric, it's the same idea. Okay, so what's good about criteria-based test design? Well, we get fewer tests than with the human-based approach, and we find more faults. So we call that more bang for the buck. We get a comprehensive test set, and there's less overlap as defined. So each criterion defines what an overlap is. It essentially takes our input space and it carves it up into regions, where each region is a set of tests that satisfy that particular test requirement. And so there's less overlap in that sense. We can trace from the software, so we have some software artifact. We created our structure, our graph, or logical expression, or whatever, and then we know where each test came from. And so if something changes, we know how that will affect each test. So that's really valuable information, especially now when we create a test once and we run it dozens or hundreds or thousands of times. Right? It's very common now for companies to run every test every day. So most of Google's software, the tests are always running 24 hours a day, 7 days a week, 365 days a year. They never really stop their testing. And you add something new into the build and the test continues, the continuous test process. We know how many tests we have. So when you go to the meeting and the project manager says, okay, Alex, so we have, how many tests do you need? With a human-based approach, he says, oh no, you have 50 to 500, something there. So when will you finish? I don't know. And the marketing guy says, well, we need to ship the software by 15 July. Will that work for testing? Sure, whatever, I don't care. But if you're basing on criteria, you're doing engineering instead of guesswork, then he says, well, we have 735 tests that we're going to need. We might be able to reduce the overlap down to about 715. It's going to take us 6 weeks. July 15, we can't hit July 15. Looks like 22 July. And the marketing guy says no. And you say, okay, well, I'll refine my criteria so we need fewer tests. And the project manager is thinking, whoa, where'd this person come from? my test manager knows stuff. And that's actually fairly rare in most, that's the way software development often works. Test managers at some companies know stuff, a lot of companies they don't, and when they don't, the software isn't as good, and the test manager isn't as successful. Okay, so to summarize, a lot of companies still use, I call it, what's monkey testing? It's like the old 10,000 monkeys on 10,000 typewriters will produce Shakespeare. Well, you know, a guy wiggling the mouse, banging on the keyboard, entering values. Maybe something works, maybe not much automation. This is the way most testing was done until about 15 years ago. You can pick up middle school kids to do this kind of testing. A lot of companies now are automating human design tests. So using test automation framework means you can run the tests repeatedly, you can check the tests, you can fix them if there's a problem, and it saves an enormous amount of resources as well as makes the test better. But a few companies are automating their criteria-based testing. What they find is that they save significant amounts of money, they find more faults in the software, and ultimately they have better software. So they get better and they get cheaper. So that's where the industry is starting to move right now. Not so much where I live, because we have a lot of government contractors. They tend to be behind the curve. This is, in the US, this is much more common on the West Coast, where there's a lot more innovation in software development. You can do especially like that one test, you can have one test that will do statement coverage, right? It's not a particularly strong test criterion. And it's better than it's more than what a lot of companies do, right? But it's still pretty weak from a testing perspective. Something like edge pair, where for every node you have to have every pair of incoming and outgoing edges in the control flow graph or whatever graph you have. That's a much stronger criterion. Prime path testing, where every test up to, but not up to and including a single iteration of a loop has to be executed. Again, that's a much stronger test criterion. Those aren't as commonly used though. And of course, anything with lots. So for the US Federal Aviation Administration requires MCDC, which is a logic testing criterion, on all safety critical software on planes that fly in the US airspace. So so it winds up being on almost a worldwide standard, because any plane that wants to come into the US needs to satisfy that. That's much stronger than statement coverage. It has some weaknesses, certainly weaker than Mutation in terms of the quality of the testing you're going to get. But it's still a reasonably good, reasonably strong test criterion. It's also been very expensive. They game the system a lot by getting exceptions. And there's lots of software that has originally been classified as safety critical that companies say, well, I don't want to spend the resources to do MCDC testing on this, so let's reclassify the software. That's a different way to game the system, right? I mean, this is not VW's gaming the system sort of strategy. I'm sure you all have heard of that, right? What kills me about that is not that the CEO wanted to cheat, but they got engineers to go along with the cheating. That's what kills me about VW's issues. So there are actually software people, they came to a software group and said, we need you to change the software so it cheats. And the engineers did it. That's what kills me. I expect CEOs to be dishonest. I expect engineers to be honest. Anyway, how do we get off on that? Yeah. Okay, anything else about criteria? Okay, let's talk about mutation, because that's why you're here. Or maybe you didn't have enough money to go on a real vacation, that's why you're here. So, what's a mutant? Well, you know, it's not a person with special powers. It's not the ability to fly or whatever. It's a small syntactic change. And the analogy is there. I mean, it comes from what's a biological mutation? It's a very small change. It's usually not the ability to fly or regrow tissue. It tends to be really small. Like, actually, I'm a recent mutant. So one of the more recent mutants was around 3,000 years, I think. So very recent in, you know, evolutionary terms, was the ability to generate vitamin D with very little sunshine. And it came with these little brown dots called freckles and red hair. Well, it used to be redder. I've been dyeing it lighter to get more respect, but there used to be more red up here. That's a very recent mutation. It's a very small mutation, but it means I'm a vitamin D factory, essentially. This actually came from Scandinavia. It was the origin. My ancestors are all Irish, which, if you know history of Ireland, it was about 1,000 years ago. There were a lot of Scandinavians, not from Sweden, from Denmark mostly, who went in and killed all the men and raped all the women. So essentially I have Scandinavian ancestry. But leaving a lot of red hair and freckles. So that's a great, when you have lots of darkness and clouds in Scandinavia, not today, but that's a marvelous mutation. It's not so good in Virginia. You know what it means in Virginia? Skin cancer. That's where I live in the South. Anyway, so to a program, it's the same, very similar ideas. Very small syntactic change, and not just to program, to lots of different kinds of programs. Java is common, but also XML, SQL, etc. We define operators, so how we make changes based on the underlying grammar. So here are a couple of examples. We change arithmetic operator, a plus to a minus, multiplication, divide. We change an edge in a finite state machine from A to B to go to A to C, things like that. Those are reasonable mutation operators. So this is a general view of mutation. We're doing mutation analysis whenever we have rules based on syntactic descriptions that make systematic changes, not just random changes, to the syntax or to the object. So a rule, that's the mutation operator. So we make this particular change. The syntactic descriptions are normally grammars. So every programming language is defined with a grammar. How many people know XML? Okay. So schemas are the grammars that define the rules for XML, right? The systematic means that we don't just make the changes randomly, which is the way biological mutation typically happens, but we make them either every possible place we can make the change, or at least some distribution that we know will give us a good collection of mutants. And the syntax means the underlying grammar is mutated, or the objects means we mutate a ground string from the grammar, a program. So a Java class, in this general sense, would be a ground string from the grammar that defines Java, for example. So these may be, we can mutate tests, or we can mutate actual programs or program components. So this is a very general, high-level picture. We're going to come down to earth. This is the fun part of mutation. We get to be violent. Computing, we don't get to be violent very often. We abort processes. But here we kill mutants. So what does it mean to kill the mutant? Well, we cause the mutated artifact to have a different behavior. So if it's a program produced this value, the mutant produced another value. That's killing that mutant. We have a test. If the test kills the mutant, cause the behavior to be different, then that's a good test. That's how we distinguish good tests. So in mutation, every mutant becomes a test requirement. So in general, mutation analysis is applying mutation operators to some artifact. We create mutants. So a mutant is an artifact, program, or finite state machine that has been mutated. All right. So mutation analysis is creating the mutants. Mutation testing is when we use mutation analysis for testing, and that's that's the most common application of mutation analysis. People are looking at others. That's one of the sort of research areas. The most common other technique now is automatic program repair. Does anybody know anything about? Have you read anything about APR? Mutation analysis is also called syntax-based testing, and there could be other forms of testing based on syntax. That's as we discussed earlier, that's the most common. Okay, so that's the introduction of mutation. Now I'm going to look at source code, and we'll probably stop here in the middle of this section. This is, I think, the longest section for a coffee break. I don't see anybody falling asleep yet. It's nice to go first. It'll be much harder about 4 o'clock in the afternoon to keep. Okay, so what is program? Well, this is where mutation started. It's the most common. In fact, the whole idea of test criteria, all the fundamental ideas started with mutation, and we realized that, oh, these apply to all our other testing techniques as well. I remember as a student, I asked, this was a while ago, my advisor, what is the difference between a test technique and a test criterion? And nobody really knew. And it was because we hadn't really gotten to the point where we fully understood what a test criterion was. That was back in the 80s, a few years ago. So program mutation, we modify the program under test. So the ground string is something that's from the grammar, right? But it's the program under test, or usually a class or a component or method of a program, not necessarily an entire program. It's important that the programs compile correctly. So if they don't compile, we throw them out. So they have to be valid according to the grammar. And once we create the mutants, then we find tests to kill those mutants. And those give us really good tests. So when we have a set of mutants, we're creating tests. Well, we have several kinds of mutants. The only good mutant is a dead mutant. So we have a test that killed the mutant that's dead. We don't have to worry about that anymore. We take it out of consideration. A stillborn mutant, so we're really pushing the analogy here, is syntactically illegal. It won't compile. We try not to generate those. So mutation analysis programs try not to generate those. And when they do, they recognize it and they take them out of processing immediately. Okay. A perfect mutation system would not generate any stillborn mutants, but we don't have that much perfection around. A trivial mutant is something that can be killed by almost any test. Right, so we make a drastic change to the first statement. So we're making small syntactic changes. We would prefer to make small semantic changes, that have small difference in behavior, but it's a lot easier to recognize a small syntax change than a semantic change in an automatic fashion. So that's sort of the difference between what we'd really like and what we get with current technologies. And then we have equivalent mutants. So what's an equivalent mutant? It's a mutant that's always the same. And I'm going to give an example in a minute. But you can think of a lot of ways to change programs where the behavior doesn't change. If you've taken a compiler class, you may have looked at compiler optimizations. A compiler optimization is essentially creating an equivalent mutant. So a change to a program where it behaves the same, but it behaves more efficiently. If you're into agile processes, you've heard of refactoring. Refactoring is intended to change the program so it still behaves the same, but the structure is better, it's more efficient, or there's something measurably better about the new version of the program. So that would be an equivalent mutant. Equivalent mutants add a lot of cost, a lot of noise, and is one of the biggest problems to adoption of mutation testing. Okay, let's look at an example. Let's get a little more concrete. So here's a simple method, a Java method, takes 2 integers and returns the smallest one. So starts assuming it's A. If A is bigger than B, then we assign B to min value and return min val. Here's another version of min with embedded mutants. So this actually represents 7 programs. And this is a common way to describe mutants, where we show the original with the modified version. So delta means the change. Mutant 1 creates a new version of min where A is replaced by B. Mutant 2 replaces, less than with greater than or equal. 3, A with min val. So each of the changed, the delta versions represents a whole different program. We just show it this so you can see how they all work. These 3, 1, 2, and 5, are variable replacement. Replace one variable with another. Here we replace a comparison operator. This is kind of interesting, bomb. So we get more violence. This is an immediate runtime failure if it's reached. Any guess why we have a bomb mutant? Think about the effect. How do we kill a bomb mutant? If we reach, exactly. So if we just use the bomb operator, then our test requirement, our mutants, our test requirements require a simpler test criterion. Statement coverage, right? So it's a mutation, it's built-in statement coverage. Make sure we get to every statement. This is a little weirder. So this isn't real Java, by the way. That's a special mutation operator. So is this. Fail on 0, which means if B is 0, we raise an exception immediately. Otherwise, we do nothing. So what's the point of that? If you've worked as a professional tester, that's probably pretty clear. If you haven't, it's a little weird. Exactly, boundary values. So a good common strategy in testing is to drive every expression to 0, because that's where we often see problems. Also negative values. So another version of this raises an exception if it's negative. So those are not common. So most of these are common mistakes programmers might make. Use the wrong variable, the wrong operator. That happens all the time. But some of these aren't. These are there to make sure we have some specific kinds of good tests. These aren't all the mutants we would have on this method, but just a sample of a few. I mean, any test set should, if you only turn on the bomb operators, then any test set should do statement coverage and kill all of those. So you're right, it's the simplest one. That's really, remember I used the term trivial mutant? That's pretty close to trivial. So the only thing you have to do here is get inside this if statement. Even more trivial is if we replace this statement with a bomb, every test case will kill it. So that's really a trivial mutant, right? This is approximately half of the tests should kill this one. So that's not a particularly useful operator, exactly right. So it's there really for completeness as much as anything else. And sometimes so we can just use that one to see if we do statement coverage. It's a rather expensive way to measure statement coverage, frankly, to use a mutation tool, but it's there. Okay, so the number 3, the third mutant, replace A with the variable min_val. Well, we can only kill this mutant. This is also a way to analyze mutants. So we can kill this mutant, B is less than min_val, if B is less than A is not equal to B is less than min_val. That's the conditions under which we kill that mutant, right? We have a different result in that if statement has a different result. The predicate changes direction. However, right before this, we had min_val equals A. So we can substitute min_val for A. So B is less than A is not equal to B less than A. That's a logical contradiction, which means that you can't kill it. So that means, assuming they're the same size, that this is an equivalent mutant. The behavior will always be the same. That defines an equivalent mutant. This, by the way, this is sort of boiled down to its essence, was my PhD thesis, was to define these conditions to generate tests. And on the way, I was able to detect about 40% of the equivalent mutants. So, 30 years from now, maybe you'll be able to summarize your PhD thesis on one slide. And then you think, wow, that was trivial. I would not award a PhD thesis for that now. Luckily, I did it back then because I couldn't do a PhD now. I'm not smart enough. So that's one of the possible values of an equivalent mutant. If you have dead code, you mutate it, you can't kill it. Is it equivalent? Well, it's equivalent because the reachability condition can't be satisfied. So this leaves off also looked at the reachability condition. What do I need to get to the mutated statement? You can't satisfy, if it's dead code, that means you can't satisfy reachability. It's hard to detect automatic. In general, it's an undecidable problem, actually. But if you can detect that, then you found something really valuable with the program. So that's one of the values of, well, most test criteria will help you detect dead code, because you can't cover that part of the code, no matter what your coverage criterion is. So they will help you identify that. And sometimes companies will leave dead code in the code base, because the concern is if I take this out, maybe I don't understand all the ramifications. So let's just recognize that doesn't do anything and leave it, so we don't have to change the flow of control of the program. To me, that's always an uncomfortable decision, but it's a decision that is made knowingly and purposefully. But anyway, yeah, so they would look like equivalent mutants. You couldn't kill them. Okay, so the Ripper model, reachability means we get to the mutated statement. Now here it's simple because it's always one statement. And we know where it is because we know what the mutant is. Infection means after the mutated statement is executed, the state is incorrect. Propagation revealability means we just observe it. So that's where the RIP model came from, was mutation, way back in the 80s. But this goes back to Mohammed's question earlier. There are two types of mutation. So we normally think of strong mutation where we require propagation. But if we say no propagation, that's called weak mutation. Now this is interesting. One of my early TSC papers was an experimental paper that found that weak mutation works very well. In the sense that if you have tests that satisfy weak mutation, so it's only infection, not propagation, you will get over 99% coverage on strong mutation. We have recent results that call that into question. I don't believe that result anymore. I think that's an artifact of how we create our mutants. And that's some of the current research that I'm going to talk about a little bit later. It's called weak because it's much easier, and you can sometimes have mutants that where the state is infected but it doesn't propagate. It gets masked in between somehow. When I did that experiment, I modified our mutation analysis engine so that we looked at, Stephen Lee did that, a master's student, did the programming, so that we looked at the internal state of the program immediately after the mutated component. So we put in a hook inside the program using the mutation analysis tool. So the mutation analysis tool was managing execution through an interpreter completely. So we're able to go in there and look at the intermediate state. And there would be other ways to do that. You could add instruments into the program to just send output at any time. Yeah. This would all affect the timing, of course. So if you're doing any sort of real-time testing, this changes everything. Okay, so we'll come back to that, but I'm not sure if weak mutation works anymore. But here, yeah, so here's an example. This is a typical mutation testing process. If you're actually going to test software, you have your program under test. You send that to the system creates mutants. If we have so detecting equivalent mutants is formally undecidable. We have a bunch of published algorithms that have gone from about 15–20% up to about 60%. That's the best one I've seen uses program slicing, if you're familiar with that. So we detect as many as we can. We generate test cases. That could be by hand or that could be automatic. We have lots of algorithms for generating tests. We run the tests on the original program, run all the mutants. These are some execution choices. I'll talk about some of these later. We throw away ineffective tests. So a test that doesn't kill any mutant, then we throw it away. We don't need that. It's not useful. Then we asked, not if we killed all the mutants, but if we got into the threshold that we care about. Maybe it's 100% we've killed all mutants, maybe 80, maybe 90, whatever you think. If we have, then we look at the program on the original set of tests. So we don't actually check the outputs until this point, mainly because we might throw away 90% of our tests at this point. If not, then we fix the program and we go back and we start again. If we haven't reached the threshold, then we need more tests. So these yellow boxes in here, we have lots of automation for this. Lots of algorithms in the literature for automating each of these steps to some degree. And equivalence detection and test case generation, those are undecidable problems. So we have approximation procedures if you're a formalist. So this is generally how we can use this in a testing system. The most efficient way to use this is up here to generate lots of tests. Just throw, if you have an engine that will generate tests automatically, just throw lots of tests at it. And maybe you get 1,000 tests, but then you run them against all the mutants and only 50 of them actually kill mutants. So you throw the rest of them away. So primarily you don't want to look at those until you throw away the ineffective tests. You could look at it after this. I mean, it could be done here. But there's not much benefit in doing it here as opposed to waiting until after you're finished. So you're always mutating an incorrect program. And so there, yeah, I mean, in a gross, so some of the easy bugs you want to find early, there may be some benefit in actually doing that here. So the process is mutable. I could see that. I want to go back to that statement before we break. If the program is correct, because this is a big deal I try to make early in my testing classes. Take the word correct. And throw it out of your vocabulary. Forget it. Mathematicians can think about correctness. Engineers don't. How many of you own a car? Is your car correct?
Correct in his life.
Huh?
Correct in his life.
Yeah, I'm going to claim it's relative to these tests, which is good point. I'll work on that at the break. Is this building correct? I don't know. I mean, we don't think about correctness with engineering artifacts. The reason we think about correct programs is because way back in the 60s, we started with a bunch of mathematicians who moved into programming, and we have this legacy. Now, I was a math major as an undergrad. I loved math, but I've sort of grown out of it. I think more like an engineer now. Engineers don't think of correctness. They think about, does it help me do things? Does it help people? Does it, solve some kinds of problems? Programs aren't correct. They're never correct. A min program can be, is PowerPoint correct? It's too complicated. Yeah, so if you have complete specifications, then you can talk about correctness. Has anybody ever created correct specifications for a large engineering artifact? Hell no, it's too complicated. It's impossible. Bottom line is we're not mathematicians. Anyway, that's a bit of rant. Now I'm sorry we take a break.